Hello, so we're going to continue our work in coordinate geometry, and today we're going to be looking at basically no new maths. We're just going to be looking at how to apply the maths we've already learned to find the centers of triangles. So there's more than one way of defining the center of a triangle depending on what you're trying to achieve. And we're going to look at a few different ways, or all of the different ways that you're supposed to know about in Leaving Cert Higher Level for the center of triangles. Now, first one we're going to deal with is called the centroid. And to find the centroid, we are going to get the midpoint of one of the sides of our triangle. We're going to draw a line through that midpoint out to the opposite vertex. Remember, a vertex is a corner. That line from the midpoint out to the vertex is going to be called a median line, and where the median lines cross is going to be our centroid. Now let's look at this in practice. So if I have my side BC of my triangle, the midpoint I'm going to call D, and we know how to construct the midpoint, and we also know how to find it algebraically. Then if I want to draw a line from the opposite vertex through D, this line here is called a median line. Now if I do that again, say if I get the midpoint of AB, I'm going to call it E, then I draw a line from E, the midpoint, out to the opposite vertex, C. This point here, where our median lines cross, is called the centroid. Now, there's a few things about the centroid. If I had this as a piece of card that I'd cut out in the shape of this triangle, that would be the balancing point. Where my median lines cross would be the balancing point, or the center of mass of my piece of card, of my triangular piece of card. So they could bring that into a kind of a real world type idea. They wouldn't require you to know that the centroid is the center of mass, but if you already know it and they're talking about it in an exam question, you'll feel much more comfortable with engaging with it. So this is the balance point, or the center of mass, or the center of gravity. There are several different ways of describing it, is where the centroid is. It's also effectively the average of the x's and the average of the y's of our three vertices. So if I get the coordinates of A, B, and C, and I got the average of the x's and the average of the y's for my 3 points, I would find the location of the centroid, and that's given by this formula here, which is not in your log tables and you are supposed to know. But if you can remember that a centroid is a central type thing, and like midpoint is the average of the x's and y's of 2 points, the centroid is the average of the x's and y's of 3 points. So that's the concept of our centroid. Now for our circumcenter, now this is something you've already come across in Junior Cert, and we need to know it as a construction as well. Now you need to know the construction of the centroid too. We have the circumcenter, and it is going to be the circle, or the circumcircle I should say, is the circle that goes through all of the outside points, all of the vertices of our triangle. So what we want to do now is find the circumcenter. We're going to find the center of this circle that goes all the way around our triangle. And to do that, we are going to get the perpendicular bisectors of each side. So I've set that up here. We get the perpendicular bisector of one side, we get the perpendicular bisector of another side. Where these two lines cross each other are the center of a circle that goes through all of our vertices. An implication of that is that the radius of that circle is going to be the distance from this point of intersection of our two lines out to any of the vertices. So this distance is the same as this distance, is the same as this distance, because they're all the radii of the same circle. And let's draw that circle in here. So that is our circumcircle. And something I want to show you is what happens if we change the type of circle that we have got. So if I move my point A at the moment I have an acute triangle. All of these are less than 90 degrees. As I move down, the angle at A is getting larger. Now what's happened at this point? My center of my circle is in the middle of my line BC. If I remember back to my junior geometry, or my geometry that I've done last year as well, I'll know that this angle must be 90 degrees because this is the BC is now the diameter of our circumcircle, because the center is on the line BC, so that means that BC must be a diameter. And then if we have a triangle that's sitting in a circle on a diameter, it means that this angle here must be 90 degrees, and it doesn't matter, we can move A around, and so long as we keep the center of our circle on our diameter line, this angle is going to remain 90 degrees. You can see it hasn't changed shape, it's still 90 degrees. Now, beyond that, if we get the angle at A greater than 90 degrees, you can see something else that happens. The circumcenter is now outside of the triangle ABC. So these are the different facts that can come up when we are dealing with the circumcenter. Now we can have a look at what's called the orthocenter. So orthogonal, we're dealing with right angles. So we are dealing with situations where we are looking for a perpendicular line or a right angle to one of our sides going up through the opposite vertex. So get a line perpendicular to a side that goes through the opposite vertex. So how would we do that? Well, we get the slope of BC and we get the perpendicular of it, and we know that the point A would be on the line. So we would end up with a line perpendicular to BC. So this is a line that's perpendicular to BC. I know its slope, and then to set where it goes, I want it to go through the opposite vertex, which is at A. Likewise, I could get a slope of the line AB, and this is a line that has a slope perpendicular to AB, and then I set that it is going to go through the opposite vertex at C. So where these two lines cross each other is called the orthocenter. The angle here, so the angle between my black line going across here and AB is going to be 90 degrees. And likewise here, the angle between my more vertical line and BC is going to be 90 degrees, and we're going off toward the opposite vertex at A. Now, if we have a look here, this has come up on the exams. One of the things that you can figure out is if when you are doing your calculations you find that these two lines cross, if you find that your orthocenter is one of your points, is one of the vertices of your triangle, that means that you have a right angle triangle. So if your orthocenter ends up being on one of your vertices, on one of your points, that means that you have a right angle triangle. And this can be a useful fact to keep in mind if you're doing exam style questions. So finally we'll have a look at the incenter. So for our incenter, now we haven't done the maths to do this algebraically yet. You know how to construct all of the things that we've shown today, that we've talked about today. You don't yet know how to do the algebra of the incenter, but I'm covering it now because you are going to know how to do it fairly soon, and I want to cover all of these ideas in one go so that you have all of the different ways of constructing a center of a triangle all together in one place for when you're reviewing it later. But you will learn how to do this algebraically as well. You know how to do everything for all of the other three ways of finding a center. You can do it algebraically and you know how to do the construction. But for the incenter, at the moment, we haven't quite gotten to that maths yet. Now, for constructing the incenter, you already know how to do this. We are going to bisect the angle at one of the vertices. So we are going to bisect the angle here, so it'd be bisecting the angle ABC, or CBA if you prefer. And then we do the same thing again with the angle at another vertex. So this is where our two angular bisector lines cross each other. And that is going to give us the center of what's called the in circle. So that's its center, and then we go out, and where it touches our triangle, that is our in circle. So this is the center of our, this is the center of our in circle, and we get it by getting the bisectors of two angles at the vertices, and then the perpendicular distance from BC up to D, our center, is going to give us the radius of that circle. So if we find the perpendicular distance from one of our sides up to our center point, then we're going to be able to find the radius of our in circle. So as you can see, for all of the different types of construction that we're talking about, in each case you know how to do the construction by hand already, and for all but the in-center, you know how to do this algebraically as well. So for the centroid, we'd be finding the midpoint of a side, and then we would be using that midpoint and the coordinates of the opposite vertex to find the equation of a median line. We do that for another side, and then find the intersection of two lines to find the centroid. That's our steps for the centroid. For the circumcenter, we know how to do all of these steps as well. So the perpendicular bisector of a side, we would get the midpoint of a side, then we would get the perpendicular slope of the side and use that to find the equation of a line. Do that for another side, and where those two lines intersect is our circumcenter. With the orthocenter, we would get the perpendicular slope to one of our sides, and then use the coordinates of the opposite vertex again to give us the equation of a line. If we do that for another side and vertex, where they intersect is the orthocenter. And then when we come to this mathematics later on, we would bisect the angle between, or the slope between, two lines, and then use the coordinates of the vertex to get the equation of a line. Do that twice, and where those two lines intersect is going to be the location of our in-center. And again, we'll come to the maths of how to do that later on. But these three here, our centroid, our circumcenter, and our orthocenter, you know how to construct, and you know how to follow the steps to, or figure out the steps to do the same thing as your construction algebraically. So this is one of the reasons why this is a really good project, these questions, because it links together constructions and algebraic steps. So if you can think through how you would construct the circumcenter, then you can do the algebra of how to do the circumcenter. Because to construct it, you'd be getting the midpoint, you'd be getting the perpendicular line to one of our sides. We'd be doing that twice and seeing where they intersected. And you do identical steps when you are doing it algebraically. So if we can visualize how we construct these things, it tells us the steps we need to do in order to figure out how to do them algebraically. So that's what we need for now.